Hi class, I wanted to go through step by step and finish working out the remainder of the problems that we unfortunately didn't get a chance to cover in class today. So we got through kind of all of our properties of powers or laws of exponents from section R2, and we got a little bit into R4, but we have some more kind of key problems or examples that I want to look through with you. So we talked about simplifying our radicals, and actually that's going to be a big thing to do in this section is to simplify these roots. That's usually an initial step, is to simplify your root and then perform additional mathematics. So we looked at this example of the square root of 48 x to the 15th, and that we could break down the 48 using our factor tree and look for factors that are essentially being multiplied by themselves, that are powers of 2. So we looked at kind of two different factorizations, but they really get you to the same place, that we have two sets of 2. So each set gets pulled out as a number outside your root. So that would be 2 times 2 or 4. With a factor of 3 left over. So the 3 would be left inside the root. So that's the key to simplifying these roots. Even if they're not square roots or say cube roots or fourth roots, you're looking for that quantity, whatever the root index is, that same quantity of numbers repeating, so that that number can be pulled outside your root. And same idea with variables. We had x to the 15th. So if I wrote out 15 x's, we would have 7 paired sets with 1 x left over. So we could actually write it out and show the pairing, but it's easier to do division in a case like that when the numbers get large. So there was 7 sets of x's with 1 left over inside the root. So now let's go ahead and look at B and C. Let me get rid of these factor trees here, or maybe just the first one, or the second one rather. So we have some space to work on this. So same idea. I want to go ahead and simplify the root 18 as far as I can before I do the other operations that are happening. So if I look at 18 as a factor tree, that is 2 times 9, and 9 can be broken down as 3 times 3. So for a square root, I'm looking for 2 of the same number to be able to pull that number outside the root. I have a double set of 3's, so I can go ahead and let me rewrite this. Carry down the parts we don't need. So there's my square root. I can pull the 3 outside, and then any unpaired values that are in my final branch of my factor tree need to remain inside. So there I have a value of 2 that didn't get paired up, so the 2 is going to remain inside my root. So that's the reduced version of root 18. It's 3 root 2. And we want those reduced roots because then now we can do more math on them. So here I can actually go ahead and do the division by 3. I can divide each of these terms by 3. It's 9 over 3 plus 3 root 3, or 3 root 2 over 3. And I can reduce. 9 divided by 3 is 3. Here the factors of 3 can cancel, leaving a root 2. So although sometimes it seems silly to reduce those roots, it really is very helpful, and that's a very important thing that we want to know how to do. The next example is a cube root. Now before I start kind of looking at the 9x squared and the 3x squared to see what I can pull outside the cube root, and we could examine that. There's really nothing, honestly. There's no triple set of the 3 of the same item that we can pull outside. The trick here is to acknowledge that we have a root times a root, and when you have the same root being multiplied, this is like this property up here on the left, not only can you break it up like we wrote out in red, but you can also combine them together. So here it's useful to go backwards, to write this as a single cube root with the 9x squared and the 3x multiplying underneath my root. And we're going to see that's actually very helpful. It allows us to simplify the roots like we couldn't before when they were written separately. So if I multiply that, 9 and 3 can multiply to become 27. X squared and x squared can become x to the 4th. And that is really helpful because now I do have some numbers and values of x that can come outside the cube root. So 27 is, from my previous step of work, 3 times 9. And 9 can be broken down as 3 times 3. So to undo my cube root, I need 3 of the same number. So here I have a triple set of 3's. So that triple set of 3 can come outside my root. So there was a 2 originally. And now I can pull out the 3 to come outside as well. Now I've used up all the values or factors of 27. There's nothing left over, so I wouldn't write any number underneath the root since all the factors got used. Then x to the 4th I can think of as x multiplied by itself 4 times. There I also have a triple set of x, and then I have a single x left over. So that single x that didn't get put as a set gets to stay inside the cube root. And then I just do any multiplication that's left over to kind of simplify this and get it down to a single result. So 2 times 3 is 6, and my x, those are both outside. Then I have my cube root with an x left inside. And that would be our final result there. Now I was just simplifying square roots so we can kind of do more math, or roots on them so you can do more math on them. Another crucial thing about our roots is that we can also have kind of like terms being added up or subtracted. We can also have like roots that can be added up or subtracted. So like in example A, here I have like roots. It's a square root of x, a y, and a z squared. This is also a square root of an x, a y, and a z squared, and a square root of an x and a y and a z squared. So these are essentially almost like variables that have coefficients that you can add and combine down to a single term. Same idea. I have the root xyz squared, and see how many there are. There's 3 of them plus 10 of them. That's 13. Then I take away 5. 13 minus 5 is 8 in total. So I would like to circle this and say it's my final answer, but there is some simplification that you got to watch for. I still want to look and see if I can reduce any of these root terms. Well, a single x can't be pulled outside the square root because we need 2 of the same value to have it come outside the root. Same thing with y. The z, though, does have 2 of the same item. A z squared is the same thing as z times z. So I can pull that z outside in front of my root, leaving just the square root of xy. So there was a little bit of simplification, and like anything, we are always trying to simplify our answers, so we always want to see if we can reduce them down in some way if we can. Now B, I'd be very tempted to say I have like terms. I see a 5th root and I see a 5th root. However, when I look at the numbers under the 5th root, these are not the same. One is a 7 and one is a 6. So these are not like roots that I can actually add up. So what can I do in this problem? Nothing. I can't do anything. So I would just circle what it was before. I mean, that's the best you can do, is write it out as 2 separate terms. Now, C, I'd be tempted to do the same thing because I see the cube root of 256 and the cube root of 32. However, these aren't reduced. In the previous example, the 5th root of 7 is definitely reduced. I don't have anything but 7, so I couldn't have enough, 5 of the same number to undo a 5th root? I don't have 5 of the same number to pull it outside. Neither do I with a 6. So those are already reduced. The 256 for a cube root and then the cube root of 32, those might be able to reduce down and become like roots that we could go ahead and subtract. I don't know that until I actually reduce it, though. So let me go ahead and look at our factors here. So the factors of 256, this is a scary big number. So the beautiful thing about factor trees is you don't necessarily have to know your multiplication table all that well. Sometimes you can just recognize like the smallest factor that you might see. Like I see that this ends in a 6. I know it's an even number, so I know it has a factor of 2 in it. And then we can use our calculator to kind of pick up the slack. So let's see. I have 256, which I'm dividing by 2. The remaining factor is 128. And maybe 128 is also kind of big. The best I can recognize is that it's even and it has a 2 in it, and that's fine. I can divide that by 2, which leaves me with 64. And again, we just keep looking for factors. So you can go for the obvious ones. That's okay. This is 2 times 32, which is 2 times 16, which is 2 times 8, which is 2 times 4, and 2 times 2. So that's fine. The beautiful thing about this factor tree method is you don't have to know the perfect square factors off the top of your head. If you do, great. There may be fewer steps that you have to go to find the paired sets. If you don't, there's nothing wrong with it. You'll still get to the number that you need. So here I'm doing a cube root, so I need 3 of the same number. So there I have a triple set of 2's, so that 2 can come outside of the cube root. Here I have another triple set, so that 2 can come outside my square root, or pardon me, cube root. And then I have 2, not 3, 2 2's left over, so it can't come outside of the cube root. So there'd still be a cube root of 2 times 2. So when it's all said and done, if I multiply that all out, it would be a 4 cube root of 4. So that's a reduced form of the cube root of 256. The next one, I'm looking at 32, so I could look at my factor tree for 32. And here's a nice cheat. I actually had it before. It was 2 times 16, which is 2 times 8, which is 2 times 4, and then I have 2 times 2. So again, I'm looking for triple sets. Here's my triple set, and that's the most that I can do. So it's still going to be minus the 4 on the outside, but now I can take the triple set of 2's that I found and pull that outside the cube root, and then I'm still going to have those 2 remaining ungrouped values of 2. So 2 times 2. So when this is all multiplied out, it's minus 4 times 2, which is 8, with a cube root of 4. So lo and behold, we do have like roots, because they're cube roots, and the number underneath the root is also a 4, so they match. They're like terms. So I can go ahead and write this as a single cube root of 4, and then you just do the operation on the coefficients. 4 minus 8 is due with a negative 4. Okay. Now we can talk about rationalizing. So rationalizing is really just dividing when we have division and our root is involved. And really the most important thing that we're concerned about is the fact that there's a square root in our denominator. We do not want square roots in the denominator of our fraction. The big reason, because you literally can't perform the division. If I didn't have a calculator that can calculate the root 3 for me, I can't do this. It's like 1 over this obscene decimal. What is that obscene decimal? Oops. The square root of 3 is that nonsense. 1.73205, on and on and on. So if I want to actually perform that division, well, I can't, right? It's 1 divided by this crazy decimal. I literally can't find a multiplier to the 1.7 to make this work, right? So that's why we don't allow square roots in the bottom, because they screw up our division, right? And we don't want that. Calculators take care of that process for us, but we're still kind of chained to the rule that we don't want a square root in the bottom of our fraction. So how do I fix it? Well, in this first example, we did not want a square root of 3 in the bottom. So how we fix that is we use that root by multiplying it by itself. So square root of 3 times square root of 3 was square root of 3 squared. So the root and the power 2 cancel, leaving a 3. And then to keep the value of what I was working with the same, we're just making it look the way we want, we need to make sure that we're multiplying by 1. So I multiplied the numerator also by root 3. So I'm left with square root of 3 over 3 as a final answer, and that's what we want. There's no root in the denominator, which is very, very good, because now if I did want to do division, right, root 3 was the 1.7, what was it, 3205? Let me look at that again. Oh wow, 3205 and on? Divided by 3. That I can do, right? I would look factors of 3 that are in 17, what is that, 15? So I could do 5 minus 15, 2, 3. I just keep on including the decimals and keep on going. Then how many 3's are there in 23? There's 7, there's 21. I can actually perform my division to some level of decimal accuracy. So that's the biggie. That's why we rationalize, so that division can actually occur. All right. So that was that first one. Now how do we handle it when it's not a single root, when we have multiple terms like the binomial? Well, in a case like this, I'd be tempted to just employ the same technique. So let's say I tried that. Let's say I had a number that I was dividing by 2 minus the square root of 2, and I wanted to rationalize it by multiplying by root 2 again. Well, it kind of fixes things, but it still creates problems, because now this becomes like a distribution problem. The square root of 2 would multiply by 2, leaving 2 root 2. So the number, if it doesn't have a root, just kind of acts like a coefficient, like 2 times x. Same idea, 2 times root 2. If they're not like roots, or they both don't have a square root, we can't combine them. Then square root of 2 times square root of 2 becomes square root of 2 squared. So that's just our root undoes our power 2, is undone by power 2, so it leaves a 2. So it fixes the square root for my second term, but then I also get a square root on the first term, and it kind of defeats the purpose of us trying to get rid of the square root of 2 in the bottom of the fraction. So just multiplying by root 2 doesn't fix our issue. So that's why we rely on really what is the difference of perfect squareds. The fact that when you have a binomial times another binomial, where the numerical values are the same, but one sign is minus and one sign plus, that you end up getting a squared number minus a squared number. So we're really using that factoring property here. What we call these guys are conjugates. So let me write that up here. So the 2 minus root 2 and 2 plus root 2 are what we call conjugates. And it's because that they're conjugates that it fixes the issue that we're having with that square root of 2 in our denominator. So let's try that. Let's try multiplying out our denominator and seeing what happens. Well, this is a binomial times a binomial. And there, how you multiply binomials is you FOIL them. So if I FOIL by multiplying all 4 terms, the first set of terms would be 2 times 2, or 4. The outer set of terms would be 2 times the square root of 2. Both are positive, so my result is positive. The inner set of terms, I have a negative 2 times root 2. And then the last set of terms, I would have a negative square root of 2 multiplying by itself, or squaring. So now that looks complicated. It looks like we are keeping our root 2's, but when you actually simplify this, it works out very nicely. What ends up happening is the 4 sticks around. My 2 root 2 and negative 2 root 2 are going to end up adding to 0 or canceling each other out. And then I am left with minus the power 2 and the root cancel, leaving a 2. So when it's all worked out, really my denominator is just a value of 2. So I've gotten rid of my square roots, which is beautiful. So multiplying that conjugate when you have a binomial that has a root in it, that's really the key. Now I've done the denominator. Now I got to worry about the numerator. So we employ that same idea that we did in our last section and in the previous problem, that I need to multiply by 1. So I'm not fundamentally changing the thing I had before. I'm keeping the same value. It just may be written in a slightly different algebraic style. So I'm multiplying that same value that was on the denominator. We're going to multiply it on the numerator. So now I have a single item multiplying by a binomial. So this becomes a distribution problem. So 2 times the square root of 3 would be the first term. And then I have on the second term a root times a root. So I can write that out, square root of 2 times square root of 3. I can actually combine those and do the multiplication underneath the root. So 2 times 3 is 6. So when they both have a root, you can actually multiply the root values together. And then here, I would be tempted to try and add these 2 roots, but they're not like roots. This is the square root of 3, which has a single factor. It won't simplify. 6 does break down, but I don't have any paired numbers. It's just 2 times 3. So I can't turn that into any form of reduced root. It's already reduced as far as it can go. So these are not like roots, so I have to leave them as they currently are. What I can do is either leave it like that as one big fraction. If you wanted to go ahead and break up your division to the 2 different terms because you're dividing by the monomial of 2, you could do that. Your 2's would cancel out, leaving the root 3. But over here it doesn't really help me much because the 6 is trapped under my root. I can't divide it by 2 because it's trapped under that root. So I might be tempted to say, oh, it's root 3. But that's not right because our square root of 6 is trapped underneath our square root. So the best I could do is write it as root 6 over 2 again. So either one of those would be a perfectly fine final answer. It's just really a matter of kind of preference. Do you prefer one big fraction or 2 separate fractions? And then one other rationalizing problem I want to come across is, what if you don't have a square root? What if you have another type of root, like a cube root? Well, the premise is still the same. I do not want a root in my denominator. And how I fix that is by in some way multiplying by that same root again. So if I multiplied the cube root of 9b squared, like we did on example A there, it wouldn't really help me much. I would have 2 of these roots multiplying together. So it's not enough, right? I need to get the cube root canceled by a power 3. So I've created a power 2. To create a power 3, I need an extra factor, or an extra multiplication. So if I did that, let's see what would happen to my denominator. Well, I would have the cube root of 9b squared multiplied by itself 3 times. That's the equivalent of power 3. So that would get rid of my cube root for me, and it would leave the 9b squared in our denominator. So that's the key. If you have a higher powered root, you would just include additional multiplications, as many as you need to get rid of your root. So here I needed the cube root of 9b squared to be multiplied by itself a total of 3 times. If I had a 4th root, then I need it multiplied a total of 4 times. A 5th root, a total number of 5 times. Honestly, we probably wouldn't go that high to a 4th or a 5th root in rationalizing, but you could see a cube root for sure. So I need to clean up the numerator. I got my denominator all figured out. Now I got to make sure that this is balanced by multiplying the same roots on the numerator. So the 6 would stay outside. These both have a cube root, so I can think of it as one big cube root with the items underneath my cube root multiplying. And so that would get me 6 with a cube root of 9 times 9, which is 81, and b squared is b to the 4th. Now I might be tempted to end here, but here's the thing, that cube root of 81b to the 4th might be able to be reduced. And if it can be reduced as a root, we want to go ahead and reduce it. So let me see if there's some numbers or some b's that we can pull outside. So 81, I remember from my previous line of work, was 9 times 9. Those can break down with values of, or factors of 3. And then for a cube root, we need 3 of the same number. I have 3 of the same number. So I can pull out a factor of 3. So let's see, I had 6. Let me rewrite what stays. Okay, all that stays. I can pull out a 3. When I look at b to the 4th, that's b multiplying by itself 4 times. I also have 3 of the same item. I have 3 quantities of b, so I can pull a b outside the cube root. And I'm left with a b inside and also a single factor of 3. So there's our cube root reduced as far as we can. And we can go ahead and clean up our multiplication. 6 times 3 is, what is that, 18b with a cube root of 3b. All divided by 9b squared. Now this is also a fraction, so we can also reduce the fraction. So 18 and 9, we can divide those and we're left with a 2. And then I also have a b on top and a b squared on the bottom. So one of those factors of b can also cancel from the numerator and denominator, leaving a single b in our denominator. And then I would be left with the cube root of 3b. And again, the stuff underneath our root, like I see another b underneath my root, I can't cancel that with the b that's on the bottom because the b that's on the bottom doesn't have a root. So this guy, this 3b, is trapped inside of the root. And that's really as far as I can go. I don't have any other simplifications or mathematical operations that I can do. All right, and then the last thing we want to talk about in this section is how we can rewrite our roots as fractional powers. So I mentioned a little bit in class how root is the same thing as a power, but we'll be very formal in explaining that and defining that right now. So if I have some expression raised to a fractional power 1 over n, that's equivalent to or this exact same thing as the nth root. So I could rewrite this as the nth root of a. And it works in both directions. Sometimes it's easier to calculate things in that nth root form. Sometimes it's easier to calculate them in that fractional power form. But they're literally meaning and performing the exact same operation. That may be helpful in a case like this one when we have a more complex power happening. So my a is being raised to the power of m divided by n. So that's the same thing as a raised to the m power and then the nth root occurring. Or I could also reverse the order. I could let the nth root happen first to my value and then let the power of m happen. So those literally mean the same thing. It's just the order in which we want the root or the power to happen first. So let's look at some of these. So on these problems we want to rewrite them from the radical form that they're currently in into that rational or fractional exponent form. So in the first one we have a cube root, so I could rewrite that as my 6x getting a 1 over 3 power. And how I knew it was 1 over 3 is because the index of my root is 3. So it's always that 3 in the denominator, and then I don't see a power on the inside, so by default it's a 1. So that cube root is the same as the 1/3 power. And then if I wanted to reduce this down some, I could go ahead and use the fact that when I have multiple items being multiplied with a power, we can let the power kind of distribute or apply to each item. So that I can let this be 6 to the 1/3 and x to the 1/3. And that's literally all that we can do at this point. There's nothing else we can do to that. So that's as far as we can possibly go. On B, we can take that same idea. I can take the 12c and I can change my root 5 into the 5th for my power, and then the 3 goes on the top. So the denominator of 5 came from my 5th root, and the numerator of 3 comes from the power. And then again, I can go ahead and use that property. I can let the power occur to each item in my multiplication. So 12 can get the power of 3/5, and so can the c. And we can't go any further with that. We're going to have to leave it just like that. And then for c, we can do the same idea. I have this 2x over y. The numerator of my power is going to be the power we currently see, which is 5. And then the index of the root will be my denominator. So 5/6 would be the power. And then again, I can, if I wanted to, apply it to each part of my fraction. The 2 should get the power of 5/6. The x should get the power of 5/6, as well as the y in the denominator can get 5/6. And there's not really anything else we can do there, so we'll go ahead and leave it as is.